Hi everyone, it has been a while since my last YouTube video. When I looked at the data at the previous YouTube video, it looked like a lot of people were interested in the actual data and the details of um, the various parameters of these algorithms. So I thought this time, the second video, I will go a little bit more into the details of the considerations around post-quantum cryptography algorithms, the consideration around hardware performance and migration path. There is a lot of I think, a little bit of nervousness that's starting because the government requirements are getting a lot closer, and people are asking what they need to do. So I thought maybe I dedicate this video not so much into the detail of how you implement each one of the algorithms, but what should you think about, what considerations should you make, and a little bit at the high level, the impact of acceleration on performance and so on. So going on, back to the CNSA 2 guidance, which is Commercial National Security Algorithm Suite. This came out from NSA back in 2022, and basically this table is based on the data in that document, and they basically set up a bunch of dates for various functions like software signing or what you need to do in your web browser or router, that sort of things, um, based on a timeline. And as you can see, the guidance was that the transition should start in 2022, and then basically anything new, any new software, any new browser or whatnot, they need to start support and prefer these algorithms. And then around 2030 and afterward, they require that you exclusively use these algorithms and give up the previous traditional legacy algorithms. So, but as far as the actual guidance, this is pretty much it as far as the guidance goes. And these are the snapshots from CNSA2, and all you can see is just for software and firmware signing, they mention a couple of algorithms and their standards. As far as symmetric key algorithms, when it comes to hashes and encryption, they're pretty much the same as before, so not a lot of problems here. There's some details related to hash algorithm. We can talk about it later. But then there are around other use cases, which is beyond software and firmware, and these are the things that you can still do around key establishment, key encryption, or digital signature, that you cannot use the mechanisms that you can use today for software and firmware, as we talk about this. So this is pretty much what you have, and you can look at it at the bottom. The specifications are TBD, or were TBD at the time of this guidance came out. The time in this guidance came out at 2022. So it's pretty hard to know what you need to do. They're not standards in this area. There's no FIP certification and whatnot. So it's good to provide some guidance, and that's what I'm trying to do as part of this YouTube video based on my experience so far. So really this video comes down to, what does this mean for me? What should I do? What should I think about? So kind of break it down into what considerations you need to make. So the first one is like, what does it mean for my business? You need to also obviously think who are your customers, and if the government is your customer, definitely you need to go after this guidance. If you have banks or you have medical customers, you need to think about these basically businesses that have compliance requirements, you need to think about it. You need to sort of think about the life of your product. And these are these two quotes that I wrote is basically the worry that people have, and basically say, okay, even though the quantum computer today does not exist, somebody can store the data and decrypt them later. And this is definitely a government and defense consideration. Is like, what if somebody listens to our communication? They don't understand it now, but when they have the right computer, they can decrypt it, and these classified documents, they can stay classified for decades sometime. So they can always decrypt it later. And I think probably the same thing will apply for banks and transactions and that sort of thing that has pretty long lifetime as far as the data goes. And something else that also coming up, I'm hearing it recently, is called authenticate now and forge later. So basically think about, you want to make sure that you have a message or a piece of code or software that you have signed now, and that way you have basically provided a guarantee for its authenticity and integrity protection. But if these algorithms are broken later, they are able to basically forge the same signature and use it on some kind of malicious code. So so those are considerations around what the data is. And a term of product, if you think about it, you may say, oh, okay, I build this product, but it's not going to last very long, or why should I worry about post-quantum when quantum computers are coming a long time from now? Let's say if you're building an automobile, this automobile is going to be out there. It's not like you have to update your iPhone or your teenager's iPhone every 2 years. This car is going to be out there for 20 years. That's something you need to think about, that these products may be out there when post-quantum cryptography becomes a necessity. So it might be, again, different compared to something like a smartwatch or an iPhone that has a much shorter lifetime. So again, what does this mean for my technology? Like I said, what is the lifetime for my data? Is it a financial transaction? Is a crypto coin that relies on a signature that is going to be broken? Or is it just, say, I'm measuring my data center temperature and want to know whether I need to set up the air condition, the HVAC or not? So that latter case, the data is not needed for a long time, right? It's you just set up the HVAC or you don't. So that's the consideration around the lifetime of the data. The other thing you kind of need to think about where I use my cryptography. So I talk about this a little bit, and what are performance requirements that I have. So just to give you an example, I have a Peloton, and sometime if I don't use the Peloton for any reason, if I go ride out my bike outside or I'm sick or something, 2 weeks later I come and I see the Peloton completely turned off. When I turn this thing on, I have to go change, I put my electrolytes together, I put my shoes on, I come back and forth and take several minutes and still haven't booted up. Yeah, I'm giving a little bit of hard time Peloton for not putting a right chip into this device that cost $2,500. Sorry, Peloton. So that means I need to think about my performance requirements. Do I want my device to really boot very quickly? Think about your car. When you put it in reverse, your camera comes up immediately. If your camera didn't come up immediately and took 2 minutes to come up, you wouldn't be very happy about your parking or your commute to work. So that's where you need to think about the performance of these algorithms. So what are the post-quantum crypto algorithms? You can think about these at several categories. So when it comes to hashing, The previous generation was SHA-2, but now we're moving to SHA-3. Not every algorithm requires SHA-2 or SHA-3, so you don't immediately have to worry about switching to SHA-3. Some do, but also remember that SHA-3, the hardware for SHA-3 runs a lot faster, and you can use SHA-3 to create a lot more random bits and keys and stuff. So that's the advantage of SHA-3, but it's not always necessary. The second category is basically hash-based algorithms, and this I talked about it in my previous video. I'm going to talk about it today in this video as well. Here, somewhere around 85 to 90% of computations are hash functions. So it's very efficient if you have accelerations for your hash functions. There are typically two categories. There's stateful functions, and these are LMS or XMSS. And then there are stateless, which are basically, you can say, Sphinx plus. LMS and XMSS are algorithms that CNSA recommended in CNSA 2.0. And the reason they call it stateful is because they do one-time signature. If you use a key pair, a public-private key pair, you can only use it once. So next time you want to sign a message, you have to remember not to use the previous key. And that's why they call it stateful. And that's why it's not a good idea to do this on the device side, because to keep the copy of all the keys that you used previously is going to take a lot of memory. So that's why government recommended this for signing, because the signing done on the server side and the device will just do verification. So if you have secure boot and those type of things, your server does these algorithms on the signing side, and the device just does verification. So on the device side, the stateless one, like Sphinx, is more preferable, but unfortunately Sphinx is not yet standardized and it's not part of the CNSA 2. But many people are already using it for performance reasons and for the fact that it's stateless. And as I mentioned, because these category of algorithm, the hash-based signature algorithms, rely on hash functions, there's less need for new hardware accelerations. The final category is what they call module lattice algorithm. They call it ML algorithm. When you see, for instance, MLDSA, which is digital signature algorithm, or MLKEM, which is a key encapsulation module. So these are a brand new set of algorithms that are designed to withstand quantum computers. A lot of people feel that these are not well understood. They're not as well understood as the hash-based algorithms. There are a lot of attacks on these algorithms, and people are worried about these attacks. And here, if you make or buy this, you have to worry about these attacks. And then they have a lot of sub-algorithms. I'll talk about this as well. So there's a lot of opportunities or challenges for accelerating all of these sub-algorithms. So, basically going back to where my needs are, and a new term is being coined as it's called cryptographic bill of materials, CBOM. You don't hear it very often. I think cryptographers like to, follow the craze around SBOM, the software bill of material, based on the White House executive order a couple of years back around creating a bill of material for all of your software. This was following the software supply chain attack that happened a few years back. So you look at your security architecture and you say, where do you need cryptography? Let's just say you need to encrypt your data in your database or your storage, basically at rest encryption. Or you need to do transport security, you need to encrypt, you need to sign the data. You have software that you need to download as far as software after update. Then you look at so these are instances when you know you need cryptography. Now you say, okay, what are the algorithms that I'm using in each case? And then it's like, what performance requirement do I have? And I just mentioned the case of Peloton. And can I accelerate? Can I use hardware to accelerate performance? And that's where delay budgets come in, and that's a very tricky design aspect that you really need to know all the steps in your design, all your basically aspects of your design to figure out, to calculate the performance, if I do it on firmware, if I do it on hardware, and so on, and do those type of considerations. And then, like I mentioned, now the other thing is, do I have security requirement? Do I want some of these algorithms to run in a secure execution environment or not? That's a very important top component as well when you're thinking about your hardware needs. So here I try to summarize the sort of a migration path. Obviously, it's very hard to just jump and people have done RSA for 30 years or 40 years now, and the elliptic curve cryptography. And by the way, I call this a public key cryptography, PKC, just to in all of these slides. So if you see PKC, it's either RSA or ECDSA or ECDH. So basically now if you think about it, you have done this for so many years. You have products out there, you have hardware out there, and now you can't just all of a sudden jump into all these new algorithms. One, because maybe you don't have the right hardware for it. Two, maybe because there are servers out there, there are customers, there are situations where you cannot have both, and there's simply people who don't trust some of these algorithms and they want to go traditional. So you kind of have to have a hybrid case, basically. So they call this the interim phase, and then finally there's a point where you just can't resist it anymore, and these are CNSA requirements. Let's say you're at 2030 and beyond, and you just don't have a hybrid case anymore, and you have moved. So if you look at it, basically, when it comes to secure boot and software update, as I mentioned, the devices need to just do signature verification. So today you use RSA or ECDSA to sign your bootloaders, your boot code, your software updates that you're sending maybe through a server or through over the air. And the hybrid solution in this case would be use the hash-based algorithm, either LMS or XMSS or Sphinx. The first two, as I mentioned, those are government requirement, and the third one is not yet standard, but lots of people are using Sphinx because of many benefits that it provides. And then post quantum 2030 and beyond, on the third column, that would be either hash-based algorithm or a module lattice algorithm. So going down, I don't want to go through all of this. I put it out there for people. I see people are a lot smarter than a YouTuber maybe give them credit for, and you can see that people just move to these slides or these parts of the video and just look at them themselves. So basically, I listed everything here based on what I think it should be a good migration path, whether you have data encryption, whether you have hash function, key derivation. As you can see, some of this don't change. AES is considered post-quantum secure, so is SHA, but SHA-2 is going to SHA-3 because the algorithms further down in this table, the module lattice algorithm, they do rely on SHA-3, so you do need to implement SHA-3 eventually. And attestation is also an area that is different from software and software update and secure boot, because attestation is something that the device makes. So you have to think about the device performance implication and the state management implication of this. So just a little bit more on, as far as table and data. This you can find in the module Lattice specifications. They're not standardized yet, they're draft. One is FIPS 203 for, I think 203 is for Kyber, and 204, if I'm not mistaken, for Dilithium. And NIST provides these security categories. So depending on the strength that you have here, they would have these security categories. I left these columns here because maybe in the future I will add more data about these algorithms. I just didn't think I had time to go through the details of these algorithms in this video. So what else as far as design consideration? I think I'm gonna maybe jump into going a little bit deeper into hash-based functions and just say what design considerations as far as hardware, just to walk you through this, design of hardware for these things. So I think I showed this. I love this picture. It's a very nice picture from this these authors. I just lifted it from that paper, and it describes the hash-based signature very well. I just don't like their parameters. The way they define the parameters with the L and all those is not standard, so I sort of tried to do my own mask, put it on there so do not confuse people. So basically, the way the LMS, XMSS, and Sphinx, they all work is they're hash-based. And the way they work is you take a message. So I'm going to define everything based on this picture. But if you're signing just one message, this is what you need to deal with. So basically, you take a message, you hash the message, and then you chop the message, the hash of the message, into a bunch of chunks. And say the hash of the message is 256 bits. You use SHA-2, and you break this into, say, chunks of 4 bits. So if 256, you think about it, 4 bits, that gives you 256 divided by 4, like 64 different chunks. So for each chunk, you look at the value of the hash at that position, and say if the value is, say, you have 4 bits, it could be anything from 1 to 15. Say the value is 3, you hash it 3 times, and that gives you the signature at that position. If the next chunk, the value is 5, you hash it 5 times, and you get the signature at that point. So on and on you go, and you do it all 64, and whatever the signature value is here, you take that value and you put them all together on all these chain, and that gives you the one-time signature, basically. So basically, you can think about this, that the smaller chunks you have, the more of these chunks you would have. Each one of these calls is called a hash chain. And why is it called a hash chain? Because for verifying that signature, let's say for doing the signature, you hash 3 times, you have to go all the way, and if the length of this was, if a chunk was 4-bit, the length of this is 15. So you have to basically hash another 12 times to get to the public key. So yeah, this is pretty hard to, I guess, understand, but maybe if you look at some of the description based on what I said, it might be easier. So basically, so this would be for one message, and then at the top here you have one public key here, one public key here, one public key here, one public key here, and so on and so forth. But then people think, each one of these is 256 bits. there's going to be a very large public key. And that's you know, I don't want to have a large public key, because let's say I sign a message, assign a bunch of messages. Normally, you in a traditional cryptography, you just have a public key and a certificate, and that's it. So now imagine you want to have one public key per message. That's going to be very expensive for many, many reasons. And it's going to be very impractical. So what people do is they put these things into the scheme that's called Merkle. There's a very smart guy who around 70s came up with this scheme. So you hash a bunch of all these things, and you come to this point, and this point is now basically one is called the root of this tree. This is a tree here, and this root would serve as a public key for all of these signatures. So yes, your signature would be this is all of this, but then if you hash it all the way here, this one hashed all the way here, all of this hashed all the way to the top, and then hash these two to get this one, hash these two to get this one, and so on and so forth. At the top, you will have only this. So this would be, you only need to calculate this to get the verification of the signature. And now people say, I don't want to have just one public key for one message, because that's not very practical. Let's say I want to put the public key inside the hardware storage for my device. So every time I sign a message, I sign a firmware, I do that. So I don't have room for putting all of this in there. So again, they build Merkle trees on top of these, and this is what they call multi-signature tree. And basically now, depending on how high this Merkle tree is, you can sign as many messages with this same public key at the top. So I hope I was able to explain this. So this kind of shows how you do any of these hash-based signatures in sort of just using hash functions. And you know, hash function is not broken, so you don't need to worry about whether this is a known algorithm or bad side channel attacks, and that sort of thing. So people feel comfortable with this because it's all based on hash function. But what about the performance here? We already see that the signature can get pretty long. And so, okay, so I mentioned all this, and I'm not going to go through this, but this kind of shows the effect of different parameters that you can choose. And as I mentioned, the big important parameter is the size of each chunk of the hash. And as I mentioned, as if the size of each chunk is too small, you have a lot of chains right next to each other. And if you but at the same time, then at the same time, is the size of the chunk is too big, then you have to go pretty far into the hash chain. I'm sorry. So there are papers around this, and they basically look at the parameters. So this is an important thing. If you use a hash-based signature, you need to choose the parameter. And you can see the papers like this where they calculate, okay, depending on this parameter, which is the size of the chunk, what happens to my signature size, and what happens to the number of operation. And you kind of see there is some sweet spot around here. You can read that paper and figure out, see why there's sweet spot there. But I'm not going to go through it. There's comparison that they make between signature size, how much I lose in signature size, and how much I gain in operation. So this is something you can go take a look when you're picking parameter size. Yeah, so the sweet spot in this case was not the sweet spot was 16. So the other thing here is that this shows that these algorithms could be further accelerated, and I'm going to talk about that a little bit in this next picture. So basically, it's the same thing as I mentioned. You have a message. As I mentioned, the message originally has to go into the SHA to get accelerated. So then you create these one-time private keys, and you feed the private keys into each one of these hash chain. As I mentioned, depending on the value of that chunk, say you hash 3 times, the signature is here, 4 times here, signature here, and so on and so forth. You need to save this as signature and pass it on when you want to say, I signed this message. And then on the verification side, you have to go hash all the way to the end of that chain. You can store it in your RAM. And then, each one of these public keys are saved. Then you do hash, then hash. There's just a lot of hashes here. So why is this interesting? Is because, first of all, this original hash of the message, there's not much you can do, because the hash function, most of the accelerators, they just take the message block by block, they bring it into the hash accelerator, but you can't do anything in parallel. But these chains, you can maybe build multiple hash accelerators next to each other and basically achieve acceleration, achieve optimization. So let's say you have multiple hash cores next to each other, you can get better performance here. And this is the idea in this paper. They're talking about the hash controller that reminds me a lot like a load balancer here, basically. And it is a load balancer. And these are all different hash cores. And these hash controllers is basically, sending data. So don't mind all of this stuff. And basically this says, you can send all this data to these different hash cores. And here basically shows the effect of, the number of cores. If you have multiple cores, you have 2, 3, 4, and so on, and this would be the effect on your performance. But obviously, you need to think about that the very first hash that you may do, as I showed you, the original message hash, that cannot be parallelized, and that makes a big difference. So what you can see that the bigger the message is, the original message, let's say you have a firmware of the size of 2 megabytes, that will diminish the return on investment on parallel hash cores. But if your message is small, or your firmware, whatever it is you're signing, maybe it's a small part of a bootloader, then you would have huge improvement, because the ratio between the number of hashes that you make in the chains versus the number of the hash that you make in the original message is very different. So anyway, that's what I mentioned. Now moving over to module lattice. So I think I was trying to basically show the impact of hardware acceleration for hash-based function. Now, as far as module lattice, I'm not going to go too much into module lattice, but I thought is a picture for people to sort of understand. The math is very complex, the standards are very complex, but the idea is basically you have a lattice. In reality is multidimensional. I'm just showing a two-dimensional lattice. And the idea of encrypting is that you have, let's say, this point on the lattice, and you multiply a small piece to it, and you add a small piece to it. These are sort of random noise, and you send this over to your recipient. And when the recipient receive it, they need to take off this, they need to take off this to come at the original message. And a lot of this is sort of sampling and figuring out, drawing random numbers and make sure these random numbers have certain properties. So a lot of times when you see performance numbers for these algorithms from your vendors, these are sort of average numbers, because there's a lot of things you have to do with these additive and multiplicative noise here. There is a lot of polynomial algebra. And so, as I mentioned, these are all high dimensional domain. They say 256 dimensions, and so you got large matrices and large vectors. You have to multiply them. You have to add them, and so on and so forth. So people are using a sort of fast Fourier transform and that type of accelerators. I call it number theorem transition or something, entity. So you see a lot of entity accelerators out there provided by vendors. And this is just the algorithm list from FIPS 203. And as you can see, there's just so many algorithms here, and you can kind of take your pick and see which algorithm is worth focusing on to improve your performance. So what are the hardware-software considerations here? Basically, I talked a lot about, hardware accelerations. Obviously, the more accelerator you add, you go from this supposed to show the effect, what happens. The more accelerator you have, more hardware, higher cost for hardware, and then you have less software, basically. So you have more stuff to do in hardware, less stuff to do in software, which means you need less memory to do all that stuff, to store all that software and run it. Typically, hopefully the idea of doing all that acceleration is that you get better performance. So you kind of have to think about this would be a trade-off, like how far do I want to go with performance improvement, and how much do I want to pay for this? And so the other idea is like this mad rush to implement post-quantum and be compliant with CNSA2. If you have a very capable team or that can build this hardware for you, by all means. But if you can, you need to think about buying this stuff. So there's a make versus buy decision that you have to make.